Okay, so another another data addressing mode is the program memory indirect. So first operand is either an implicit R0 or a GPR address, and second operand is implicit Z register. So word address is Z15 down to 1, and byte offset is the least significant bit of it. So what do we mean by that? We can have either program memory constant addressing, where this is the Z register, 15 down to 1. And then we have got one bit, which is the least significant bit of it, of the Z register, is used as the byte offset of the program memory. So this is the program memory. And in that program memory, we have got 15 down to 8. And 7 down to 0. So this is actually divided, the low byte and the high byte of the program memory. And from the Z register, we can actually indirectly reach that point by using only the least significant bit as a point over here. So when it is 0, it's pointing the low byte. When it is 1, it's pointing the high byte of the program memory. Okay, so for example, we have got 0, 0, 0, 0, 0, 0, 2, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, okay, 14, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now the 15th, when it is 0, it's pointing this one. And if I repeat that, when it is 1, it's actually pointing this part. And then this can go to any point. It is 1, 0. It's again pointing the next address on the low byte, and 1, 1, then the next address on the high byte, and so on. So this is how we can use program memory as a constant addressing. The instruction is LPM, load program memory or store program memory. And SPM is not covered, but if first operand is implicitly R0, then the instruction does not have any operands. That means that it is using implicit addressing for both source and destination. It's one word, but it's 3 cycle. LPM also has an auto increment version. Now with the auto increment version, we just need to modify the register over here, where we can have the plus sign to fit in the Z register and +1 here. Okay, and that is post increment 15 down to 1 again, and then 0 bits, which is fed in, which is the LSB. And this is Z register. This is 16 bits. It's covering all. Now this 15 bit is going in to the data space. So it's actually pointing the program memory space. So 11 bits is the opcode, and 5 bits are the register that we use to define it. So for example, LPM RN Z instruction load the byte pointed to by Z into the RN. And in AVR, each location of the program memory is 2 bytes, as I already defined over here. So we should mention if we want to read the low byte or the high byte, and that's coming from the least significant bit of the Z register. So whether we want to read the low byte or the high byte, if least significant bit is 0, then it's the low byte, as I demonstrated over here. And if the least significant bit is 1, then we have to do the high byte read. And the instructions are LPM RDZ and LPM RDZ plus. So with post increment. Okay, so we also have indirect program addressing. So what is indirect program addressing? You can also call this as an implicit as well. IJump, ICall, which we have covered. They are one word and 2 cycles. There's no operand. So Z register is implicit operand over there. So program counter jumps to specified point by the Z register. And direct program addressing, call, jump, which are 2 words or 3 cycles. They are having a 22-bit operand in the program memory space because we have to jump to a specific address on the program counter, and they are all specified with jump and the constant with the address or call, and they can be between 0 to 22 bits. So that's coming from the program counter. Okay. So these are all the addressing modes. You have to learn these, and you don't need to memorize any of the machine code formats, but you have to know which one to use when. So, and which addressing modes we are using for each instruction. That's quite important. And next thing that I want to cover is the relative. So RJump branches, they are relative program addressing. And its words is 1 word, 2 cycles. Operands are generally 12 bits. So k is between -2 to the power 11 to plus. We can go negative branch, negative jump or forward jumps, positive jumps. And R jumps and branches are similar conditional statements, and they are short jumps actually. And these are their machine code formats. Right, so when we have got a assembly code, how can we disassemble that? Or how can, if we have a code, how can we convert that to an assembly language or assembly code? So this is important, and this is what I want to cover next in order to demonstrate assembling and disassembling a code. So it's not something easy, and you just need to refer to the datasheet in order to find out the machine code formats for the when we are decoding it. So there are some hints that we can find out on this map over here. So if it's starting with 0, 0, there are 2 alternatives. Either it's a 2-register direct or no operation, or single register immediate operations that we need to perform. And if it is 0, 1, then it's a single register immediate. If it is 1, 1, it can be single register, or it can be program relative, or it can be unconditional and conditional. 1, 0s are generally IO direct, and if it's not 1, 0, that means it can be implicit, single register direct, data program memory, and so on. And few notes over here. In general, memory load store starts with 1001 and then 00. but there is 1000 and 00 exception, perhaps the others. And memory load store instructions, bit 9 is 0 for load and 1 for store. And indirect instructions, bit 3 and 2, 1 for X, 10 for Y, and 00 for Z. And memory indirect with displacement, bit 3 is equals 1 for Y and 0 for Z. And these are just rough observations, and there can be an exceptions. So I want to show you a simple disassembling example which we can go through together in order to understand how we can disassemble it. So the addresses are given, the hex values are given, then we will convert this to binaries, and then from the binary we will try to understand which machine code is written over there. So the first one is at address 0100 is E100. Now E100 is E is 1110, 1 is 000001, then 0000 and 0000. Now this is the binary equivalent, binary hex. Then we have got E3A0, again 1110, 0011. A is 1010 and 0000. Then we have got E0B1, which is 1110, 0000, then 1010 and 0001. And then we have got E6C0, 1110, 0110, 1100, and 0000. This is E6C0. Then we have got E0D0, 1110, 0000. D is 1101, and then 0000. Then 914D, so 1001, 0001, 0100, and 1101. Then 934D, and that's going to be 1001, 0011, 0100, and 1101. And 950A, 1001, 0100, oops, 0101, 0000, and 1010. And the last one is F7E1, which is 1111, 0111, 1110, and 0001. So these are all the instructions. Now, let's check what we have got over here and how are we going to deal with this. So the binaries are given. We have found it already. So where to begin? Now, you can check from the data sheet that we can easily find out what each of these instructions are. Generally, we start with LDI. So we can see how these are going to be mapped. It's actually coming from a experience after a while when you look at the first opcodes. So 1110 is actually giving us single register immediate instruction, which is LDI, CPI, NDI, and that kind of instructions. So that means we have to look at those. And then 1001, so 10s, we have got them. They can be implicit, they can be single register direct, they can be data program memory or register pair immediate. It can be any of those. And 11111 is program relative, so it's like a conditional, maybe a jump or maybe a branch instruction. Okay, so once we understand what we are looking for, we can see that these are all, as I mentioned already, these are highlighted. And based on that, we can have this formation. So LDI format, LDX, ST, decrement, and BRNE. You can find these in the data sheet. I'm just providing them now so that we can disassemble the code. Okay then. So if we look at the first one, 1110, 0001, 0000, and 0000. Now, over here, I can see that these are all 1110s. So this means that these are all LDI instructions. Okay, so these are all LDI instructions, and we have to understand what they are. Okay, so opcode is given 1110, it's LDI. Now, when I look at this rest 4 is our K constant, and that is also constant. Okay, and in between that, so I will highlight this as a green and this one as green, and this will be blue, which is 000. So what we have said about LDI instruction, when everything is 000, because LDI is using 16 down to 16 up to 31, that means 000 is R16. Okay, so we are actually saying that the first instruction is LDI R16, and we have to find the constant now. It's 1 and it is 0. So what's that? It is just 0 hex 1 0. Okay, so this is given to us, or if it's all together, maybe we can think about it like that. It's 1 0 actually. Let's write it like that. Let's keep it like that. So then we move to the next one. So this is the constant, and this is going to be the destination. Now, what is 1010? 1010 is, if R16 is 000, 1010 is 10. So 16 plus 10, this is actually going to give you R26. Now, R26 is actually what? It's actually our register Z. So here I can say that LDI, it's going to be R26, which is X, let's say, and it's going to be 011 is 3, 000 is 0, so 0 hex 30. Then let's look at the next one. 000 001. So this is 0 hex 01. And again, it's pointing X register. So this is an experience, but I can understand that if both instructions are pointing to X register, that means one of them is pointing to the X low, another one is pointing to the X high. X low, X high, LDI. Okay, so the first four instructions disassembled. Then another LDI is doing what? It's doing, we have got 6 and 0, 0 hex 6 0, and it's pointing to an address 1100. So again, if it is 00 is R16, 1100 is going to be 16 plus 1100 is 12. 16 plus 12 is 28. So this is R28. What is R28? R28 is register Y. So register Y, by the way, just a short mistake over here. This is going to be 1, and this is actually showing that it's going to be R26. That's R27. And then 12 is R28, and this is R29. So it's actually specifying that this is going to be Y low and Y high for the next one, which is the value becomes 000. So 0 hex, oops, 0 hex 00, LDI, and LDI for all those. Now, we completed LDIs. Then the next one is 1001, 0001, and then 1101, which is LDX with post increment format. Okay, so what is LDX post increment? I'll change the color because these are all 1001, but this is as 1101, it's LDX. So LDX post increment is actually specifying us that this D is giving us the GPR that we are going to increment. So I'll select that, and this is going to be 10100. So what is that binary number? That is actually 20. So I'm just writing next to it, if I can fit in over here for this instruction. This is load. This is GPR register R20 because it's saying 20, 5 bits, R20, and we have to do X with post increment, so it's just X plus. Then the next one, 1101, and then it is doing so 0011, and this is 9, sorry, 9349, 9349, sorry, I made a mistake over here. That will be 001. Now this is actually specifying it's a store instruction. Store instruction to where? Again, this is going to be GPR. So which GPR is that? It's also R20. Now that means I have to write store from where. That is important. From where we are storing, from Y. So that means storing to Y. From where? From R20. So R20 on both, one of them is loading, other one storing, one of them is using X plus, other one is using Y plus. Then if you carry on analyzing it, again 1001, and we have got 1010, which is decrement. So we can see that this is going to be a decrement. And decrementing what? One zero 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 zero, which is 16. So we have to decrement R16, which is the counter in this case. So after the decrement, we have just got BRNE, which is branch not equal, and it's obvious now. And all we need to do is we have to specify where we are going to jump. So that's the important point. So if I get that out, starting from the second bit over here, going down to here. Now we know that this is going to be BRNE, but where do we need to jump? We have to calculate that. Okay, so in order to calculate that, we have got, I'm just going to write it over here, 1, 1, 1, 1, 1, 0, 0. So what is this? This is actually, when you think about it, if you take the complement of it, you can find the exact value that we need to go in. So it's going to be 0, 0, 1, 0, 0, 0, 0. So this is actually giving us 4. And we know that with the branch instructions, program counter goes to the next instruction. So that means it has to be program counter equals program counter plus 1. So that means 4 plus 1, it's going to be 5. But as this is minus, we have to do a backwards jump, 5 steps. So backward jumps, in this case, it's going to be what? Sorry, this is minus 4 plus 1. So this is minus 4 plus 1. It's going to be minus 3. So backwards, 3 jumps. So let's see what's going to be that backwards 3 jumps. So 1, 2, 3. We are jumping backwards 3, and that will be where we started with load. So this is going to be L1 and L1 at that point. Okay, so backwards 3 jumps is actually specifying that we need to go to load R20 X plus. So this is how we can use disassembling, and we can operate it. This is just an experience, so you have to get used to it with the formats and the instructions, and then you can get out from it. You can see that this is LDI format. Okay, this will be the destination, this will be the source or the constants, and you can dig it out. And don't forget it, you can always use your data sheets for the instruction formats.